Hi, my name is Georgi Radulov, and I would like to discuss with you the inverter-based two-stage current mirror operational transconductors amplifier, and I will exemplify the design of such an amplifier by targeting a DC gain of 60 dB and unity gain bandwidth of 500 MHz. This is here the architecture that I would like to discuss today, and it is composed by two stages. So we have here the first stage, which is differential to single-ended amplifier, and the conversion is realized via a current mirror here with certain copying ratio 1:1. And to get more gain at low frequencies, we use a second stage. So this is the first stage, and this will be the second stage. So the structure is biased here by this bias generator, which is a self-biased inverter, and the input is AC. For AC signal, it's coupled by these capacitors, AC coupling capacitors, which actually isolate the DC component of the input voltage here from the self-biasing. So for self-biasing for DC signals, we get the biasing from this bias block generator, and then we couple it through some resistors to these nodes. In this way, the inputs of the transistors, the input pair transistors, are biased at a proper operation point. And with the AC coupling capacitors, we get the AC component of the input signal. Then how does this work? Here, if say the voltage here increases, this causes increase of the current. So this current, the drain current, will increase by a value of so GM times V in, say this is V in plus, the change of the V in plus, and this is actually the change of the current. Now, if this this voltage increases because this is a differential input signal, then this will decrease, and then this current here in the other branch will actually be modulated in the opposite direction. All right. So now this the left current will be copied by the current mirror, and at this node, which is the output of the first stage, we will actually subtract this to current, because you see that the modulation is in the opposite direction. So the excess current will have to be translated into voltage through the resistance at this node, the resistance level of this node. What we see here in one stage is that first we transformed the current to the voltage to current through the GM of the transistors, and then this is GM, and then the second operation is that we transform the current back to voltage through a certain equivalent resistance. And in this case, the equivalent resistance is the equivalent resistance of the output node of the first stage, which is intermediate node for the whole amplifier. Then we realize some amplification, say about 30 dB, and we use another stage in order to boost further the amplification. And in this case, the other stage is first of all again AC decoupled, DC decoupled, AC coupled. So we block here the DC component, because this common mode of the signal here, biasing point, does not mean that it's optimal for the second stage input. So this is why we decouple for AC signals the input stage and the output stage. And the biasing for the second stage is realized by this resistor, which is a self-biased resistor, self-biasing approach. And in this way, we guarantee that the transistors of the second stage will be biased at an almost optimal operation point. Then we have here, this is also an interesting thing, we have a Miller compensation, and this Miller compensation is used in order to stabilize the amplifier. Why we need stabilization? The reason is that we have two dominant poles, so basically this one and this one for these two nodes, and they will rotate the phase almost at 180 degrees. Then if we use this amplifier in a feedback configuration with negative feedback, there is a risk that this negative feedback becomes positive because of the phase rotation of that we have in our amplifier. So this is why we use here Miller compensation. Yeah, this is the amplifier. So let's see how we analyze it further in more details. Now the first thing is the biasing. I want to discuss the biasing. So basically here all AC signals are essentially removed, and all AC paths are removed. So to concentrate only on the way we bias the transistors. Alright, so here we have a self-biasing inverter, so it generates its characteristic input-output characteristic of its transistor is something like this, like an inverter, and the characteristic of the resistor here, self-biasing resistor, is something like this, input-output. So this will be then in the middle the generated solution of these two paths through the resistors and through the transistors and through the resistor. So this voltage now is generated and is fed here through resistors to the gates of the input of the amplifier. So now we know that these transistors, because they will be very much similar to this transistor here, these two transistors, the input differential pair, will be biased at an almost optimal operation point, which is this one, of course. So then we have here an output voltage, but this does not mean that it's optimal for the second stage. So this is why we'll decouple it for DC from the first stage, and we'll use self-biasing to generate on bias. So the self-biasing principle is like this, and this guarantees that this structure, the second stage structure, operates also at an almost optimal point. Now for AC signals, the structure looks like this. Now what we have here is that we removed the structures that are responsible for DC biasing. Now we concentrate on AC signals. The input capacitors, the AC coupling capacitors, are extremely large, so that even for low frequency AC signals their impedance is 0, and then we can consider this as short circuits. Now this is how the two-stage amplifier looks like. At the input we have a differential stage, and the first stage is meant to provide a gain of about, say, 30 dB, and then if we have in the second stage, say, about 30 dB, we have total then gain, the total gain for very low DC gain for very low frequencies will be then A1 times A2 will be 60 dB. So this is the goal. Here you see that the first amplification is this, and then we have further amplification. Now 60 dB is quite a lot of gain, because this is 1000 times, 1000 times gain of the signal. Now what is this gain about? So for the first stage, you see, is the common source amplifier, and the second is common source amplifier. So for common source amplifier, the gain in the most generic case is the equivalent GM that we have of the stage times the equivalent resistance of the stage, and A2 is respectively GM2 R equivalent 2, so this is R equivalent 1. Now the GM of the first stage is given by GMN. This part here is responsible for the translation of voltage to current, and the transistors that do these translations are here the input pair transistors, and then the transformation is through GM. Now this current is modulated and it's passed here in these transistors. So if the structure is excited with differential signals, then here this modulated signal and this modulated signal will be in opposite direction. So the excess current will be transformed to a voltage fluctuation by the equivalent resistance. So now at the equivalent resistance at this node will be the channel length modulation of the PMOS and the NMOS transistor. Say this is arrow P and this is arrow N. So R equivalent will be arrow P. So the same here, except that now the amplifying transistors are both the P transistor and the N transistor. So this means that GM2 is actually GMN plus GMP. You see that both transistors contribute to the modulation of current. Say this voltage changes, then this current here in this direction increases, while this current in this direction decreases. So again, excess current is generated. But essentially, both the P and the N transistors participate in the formation of GM. Let's see how the gain behaves for low frequencies. We have here the differential. It's multiplied here, so it will be GM1 times R equivalent 1, and this is GM2 R equivalent 2. Now, very important to note is that we have a pole here. So this means that this gain will reduce at high frequencies, and it will reduce at high frequency by the effect of the pole, T1, where the time constant of this node, T1, is, of course, the equivalent capacitance at this node times the equivalent resistance at this node. The equivalent capacitance will be basically the sum of all parasitic capacitances here and the load of this. So this gain will also reduce with the time constant of the second stage, where the time constant of the second stage is C equivalent to R equivalent 2. This is 1 and this is 1. So now the equivalent capacitance for this node, of course, will be dominated by C load and capacitances. Now let's see the Bode plots without the Miller compensation. So this here, you see here, this capacitor is the Miller compensation, and we use it for the frequency stabilization of the whole structure. So for now we will ignore it to see what's the problem and why we need to use Miller capacitance. Alright, so now what we have here, we have first let's write down the gains. A1 is GM1 R equivalent 1, A2 R equivalent 2, and now we have here the time constants. Say tau 1 will be R1 R equivalent 1, C equivalent 1, and then tau 2 will be R equivalent 2, C equivalent 2. Now these time constants will determine the poles. So if I look the gain at J omega, it will be of course A1 divided 1 plus S tau 1, which means that there is a pole frequency that is related to the time constant. The same here with the second stage. Now the problem with the pole frequency is that alright, so of course the gain, so say the total gain in frequency domain, so say this is omega, will be something like this, alright, where we have the frequencies omega p1 and omega p2, depending on how we design this. Now, every pole frequency, of course, reduces the gain in the frequency and then introduces per decade. So here we will have reduction of the gain of minus 40 dB per decade. That's clear. But what's also important to note is the phase rotation of the gain. And the phase rotation of the gain is that, say, at low frequency it is 0, but then for every frequency here, so say this frequency here, we have, due to this pole, a total rotation in the frequency of minus 90 degrees. So from low frequency to infinity frequency, every pole contributes minus 90 degrees. Exactly the pole frequency, it contributes exactly 45 degrees. So this means that around here we will start rotating the phase, something like this, and then this will be the phase contribution of this pole. But now you see that the second pole will also rotate, so it will add to the phase rotation further, and there is a risk. So here we'll complete the 90 minus 90 degrees and then minus 180 degrees, and there is a risk that the two poles will get very close to the minus 180 degrees, and this is a very dangerous situation, because then the transfer from input to output becomes almost inverted. 180 degrees phase rotation is almost inversion, which means that if we use this amplifier as together with negative feedback, this negative feedback will become positive feedback with additional parasitic phase rotation in the negative feedback, and then it will become an oscillator, so unstable system. So this 180 degrees gives us a very important boundary, because we need to in the phase for a stable system, we need to have total phase rotation from the input to the output less than 180 degrees at the frequency of the unity gain bandwidth. So this is the unity gain bandwidth when the gain becomes 1, so in dB scale 0 dB, and then at this frequency called ft, we must have phase rotation that is total phase rotation that is less than 180 degrees. Then we will have a stable system, guaranteed stable system. Now that's a problem, because these two poles are very close to each other. Why? They are, if you look at the expression how they are constructed, the poles depend on an equivalent resistance and on some capacitance, equivalent capacitance. Now the equivalent resistance is in the same order of the first and the second stage, because it's simply arrow P in parallel with arrow N, yeah, in both cases. And C equivalent, you see this, we use the same capacitances and we use the same we use the same transistors that have similar parasitic capacitances. So there is no real reason why in this configuration, with this architecture, one pole should be much different than the other pole. And then we'll have, if they are close to each other, they will have similar phase rotation, and then both poles will contribute to the total phase rotation, and by the unity gain bandwidth ft, we may go into risks of total phase rotation close to 180 degrees. So what's the solution for this? The solution is this capacitor, this small capacitor called Miller capacitor. So what happens with this capacitor is that The equivalent capacitance that we see at this node, so basically looking at this node here, is much bigger. So if I quickly just redraw equivalent circuit of the output stage of the second of here of this node, the internal node, so I have these transistors, and then I can represent these capacitors, say the Miller capacitance, with certain equivalent capacitance. And this capacitor will be very big. Why? Because there is the Miller effect acting on top of CM here. So what's the Miller effect? You see here that from this stage to this stage I have enormous gain, which means that the effective voltage change across the terminals of the capacitor is much bigger than just the signal. Why? Because first we invert the signal and then we amplify the signal. So the equivalent capacitor, which is from this node to ground, is actually multiplied by the gain of the second stage. So then the capacitor will be Cm times 1 plus the gain of the second stage, and this is called the Miller effect. The Miller effect makes this capacitor to look much bigger than it actually is. So now remember that A2 is about 30 dB because it is GM 2 times the equivalent resistance of the second stage. So then if this capacitor is very big, this means that the time constant of the first stage, R equivalent of the first stage, becomes very long, which means that omega p goes to lower frequencies. Alright, very well. So this means that for the phase now, for the phase rotation, the first pole is already at a very low frequency, and then the phase becomes rotating here, then it completes its rotation minus 90 degrees, and the gain actually starts reducing at a much earlier frequency. So it has it has the space in order to cross here the 0 dB level, or the unity gain bandwidth, before the effect of phase rotation of the second pole. But what's going on with the second pole? Now the second pole, see, let's concentrate on this transistor. So just this transistor, but the arguments are also valid for the other transistor. So we have this configuration, and the second pole, omega p2, is 1 over the equivalent resistance of the second stage and the equivalent capacitance of the second stage. So the equivalent resistance of the second stage, if you look at high frequencies, the impedance of a capacitor reduces. So at high frequency, let me take another color. At high frequency, actually I can represent this as a shorted signal, like this, at high frequency, because the impedance of the capacitor reduces. And now this, like a configuration, looks like a diode connected transistor. So this R equivalent goes actually as 1 over GM, because this is the impedance of of an amplifier, of a diode connected transistor. The same is valid also for the PMOS transistor, by the way. So the equivalent resistance actually of the second stage, goes as 1 over GMN plus GMP, which is very much reducing it. So now the equivalent resistance in the presence of this Miller capacitance drops down, which means that if this reduces, then the second pole frequency increases. So then the second pole goes to much higher frequencies. And now the phase rotation due to the second pole starts at very low frequency, at very high frequency. So this means that we can, up to the unity gain bandwidth, we can have a system which behaves like a single pole system, single pole amplifier, which is a stable amplifier. Alright, so let's now see an example of how we design these structures. So this is the design that we have. I have already built it in Cadence. How to do this, you can consult with my previous videos. So what we have here is the input power supply, 1 volt. Usually for this integrated circuit technology of 45 nanometer CMOS, we would use 1.2 volts. But I intentionally designed with 1 volt to leave some margins for further optimizations if needed, and also to make the illustrative example a little bit more difficult. So 1 volt, and we have the first stage here, which is a current mirror stage, current mirror OTA, and we realize gain here, and then we pass it to the second stage, which is AC coupled. This is a DC blocking capacitor, so that we can use our own biasing point for the second stage. And this is the second stage. The load is 10 femto. So here is how the input differential signal is generated. It is AC coupled to the first stage, and the biasing is for the first stage is provided by this link through these resistors. So at DC, for the biasing conditions, this path is cut because of the decoupling capacitors, and then we get the voltage at the input of the input transistors, differential transistors, through these resistors, this one and this one. This is how they are biased. Now there is room for optimization in the biasing stage 2, because this is not an inverter, because the load here is diode connected. Now this means that we can choose a better biasing point for the NMOS transistors. The biasing is not optimum, but it is close to the optimum. Then we will run now an AC simulation. So everything is set. You can see here the parameters, number of fingers 64, the unit length is 0.9 micro, and the unit W is 500 nano, and then the total width we will scale with the number of fingers per transistor. So we have now the Miller capacitance for stabilization. I'll start with 0 in order to illustrate the problem, and then I'll run AC simulations to generate the Bode plots. Bode plots are generated with these two formulas for the magnitude. I take the magnitude of the output signal V out, and I plot it in dB scale, and this is the phase. This is how it's taken, the phase of the input signal. So okay, now let me run the simulations. So this is the Bode plots, Bode magnitude transfer and Bode phase transfer. Let's do it. So at DC we have 60 dB gain. It is good to create a vertical marker. So you see that for low frequencies the gain is 60 dB as our specifications, and then the first pole will be around 57 dB, something like this. So this is the first pole, minus 3 dB frequency, and then you see that the phase rotation is minus 45 degrees. So now the unity gain bandwidth frequency is interesting, and this is about here, the unity gain bandwidth. We have a unity gain bandwidth of 1.3 gigahertz approximately. So this is the range of frequency for which the architecture is amplifying signals, and beyond this it cannot amplify anymore, and actually it acts like attenuator. And then at this frequency you see that the phase rotation of the phase is 179.6, almost 180 degrees. So basically then the structure is not really stable when used with a negative feedback, because effectively the phase rotation adds an inversion, and any negative feedback when used with this amplifier will become a positive feedback, and then it will not be a stable system, but it will act like an oscillator. So to compensate this, we'll have to sacrifice some of the bandwidth, and we can do this through the Miller compensation. What the Miller compensation will do, it will bring the 3 dB frequency through the pole associated with this node to lower frequency, and it will bring a second pole associated with the output node to higher frequencies. So let's try some values, like say 150 femto for the Miller capacitor, and then I can run the simulation. And now you see that first of all the unity gain bandwidth frequency moved to lower frequency. So if I look at 57, something like this, it's now 1.4 1.5 megahertz. Then what's very important is the unity gain bandwidth, and this is when the gain in dB scale becomes 0, or linear scale 1, so this. And now the phase rotation is almost 170 dB, which means 170 degrees, which means that we have 10 degrees margin for the phase rotation. If you now want more phase margin, you can increase the Miller capacitance, or you can optimize further the settings. So one optimization can be also the biasing level of the first stage. Further, you can optimize this architecture by choosing different gains for the first stage and for the second stage. For this demonstration, I have chosen absolutely the same W and L sizes for all transistors, PMOS and for NMOS transistors, and they are common for all units here with these values. Now this is not optimal, of course, and you can further optimize it by allocating different gains for the second stage and for the first stage. You can also optimize further, of course, the power supply range, and you can if you design for real integrated circuit, then the decoupling capacitors and the decoupling resistors must have also some realistic values. So for the resistors in the kilo ohm range, and for the capacitors in the hundreds of femtofarad range and the picofarad range also. But I intentionally chose not to do this in order to concentrate on the AC design. Thank you very much for your attention. Bye bye.